You ready then?
Yeah, I'm started the recording. Thank you for joining us. This is the evening of Python coding, the online version, because we couldn't meet because of the virus. However, we will be still talking about the SAT solver library, Z3. And actually, who's gonna talk is Silas Barta, and I'm gonna pass it to Silas. Silas, go ahead.
All right, thank you, Jacob. Well, I'm happy to be able to talk about SAT solver libraries, and in particular Z3 for Python. It's a really interesting topic for me because when I learned about them, it's like, wow, you have this superpower that lets you solve arbitrary constraint problems. Now, in the announcement, it was mentioned as a Z3 as being a theorem prover, which it also is. But the main thing that I use it for is the fact that you can take any kind of constraint or optimization problem, plug in your constraints or what you're trying to optimize, and it can exploit the power of SAT solvers under the hood to quickly find a solution. And I'm going to take you through a little bit of how they work and how you would apply them to a practical problem. As I said earlier, please jump in and ask questions anytime. Also, there are those three setup commands to start the process for the Z3 library to install. It takes a while because, at least on my computer, I had to compile it, which is a really long, involved process because it's trying to be really efficient, trying to compile the most efficient code it can, uses a lot of C optimizations and whatnot. So, without any further ado, what is SAT and why does it matter? SAT is the Boolean Satisfiability problem, which is given a logical expression on Boolean variables, find a true or false assignment to each variable that makes the expression true. I have a small toy example right here that you have this expression. It's three things ANDed together: A or B, and B or not A, and not A or not B. And that happens to have a solution. If you set A to false and B to true, then each of these clauses will be true. What's important is that SAT is an NP-complete problem, which means it's equivalent to a large class of interesting problems. Efficient routing, circuit design, Sudoku, traveling salesman. It's just a matter of being able to convert one into the other. So as long as you're able to phrase your problem in a way that the SAT solver, phrase it as a SAT solver, then you can exploit the tremendous power that these SAT solvers have to find a solution. And the SAT libraries like Z3 have a bunch of utilities that help you to express your problem. As long as you can model your problem and express it in the terms, then it can efficiently find a solution. So to give an example of converting it into the language of a SAT solver, there would be you might be dealing with an integer inequality as a constraint. Let's say you wanted to say A is greater than B. How does that get converted down into a SAT expression that these SAT solvers are really good at? Well, in this case, you would break it down into some binary expression. Do we have a question?
Excuse me. You said you're going to still do your thing and you'd be unrelated to working your project.
Now? Let me go back to the video. I didn't quite catch that. Could you repeat that?
I think there's someone mistakenly joined in and joined out or something like that.
So you get messages.
Yeah, I don't know who asked the question. I believe that you can.
All right, I will continue on. Okay, so anyway, if you were converting an integer expression like A is greater than B down to a SAT expression, how would we do that? Well, you'd represent them in binary so that there are individual, so that the numbers are made up of Booleans, and then you would basically convert it. Imagine you're comparing two binary numbers or even decimal numbers. How do you do it? Well, you look at the most significant digit. If they're equal, you look at the next digit. Concretely, if you were looking at 2 bits, and this generalizes, let's say the higher bits are A1 and B1, the lower bits are A0 and B0. To convert that into a Boolean expression, you would be basically saying, you would be expressing that as A1 is 1 and B1 is 0, or A1 and B1 are the same, and AO is 1 and B1 is 0. Just a complicated way of saying, first check if the bigger binary digit on A is bigger than the bigger binary digit on B. If they're equal, look at the next highest bit. And there's this Boolean expression right there to show you what it would turn in down to. And of course, you could convert it, convert it into an equivalent expression even further. And the good news is you don't have to actually see that expression. Once you have one of these sat libraries, all you basically have to do is tell the sat solver that you have A and B as integer variables, and then you add the constraint directly as A is greater than B. Another example, let's say you wanted to say add a distinctness constraint. That is, you have A, B, and C, and they all have to be different values. You would express that logically as A is not equal to B, B is not equal to C, A is not equal to C. Use the same trick, break them down into binary values so that you have them as Boolean variables. And then you can break down that equality in a way that is representable as a Boolean expression. So you would say, like, the high digit of B is not equal to the high digit of A, or the next highest digit of B is not equal to the next highest digit of A, and so on down the line. Basically, they're only equal if all of the binary digits are equal. So that's how you would express it for the Boolean solver, for the sat solver.
Silas, just to understand, A and B without the subscript, those are binary numbers, and when you say subscript, those are booleans, correct?
Yes. You would think of BN. BN would be a boolean, 0 or 1, and then you combine them all together to make to represent B.
Okay, so the streams I see on screen, like AN to A0, this means all the digits, the digits of the binary number, correct?
Right, those are all the binary digits of A.
Okay, so, okay, now it's more understandable. Thank you.
Cool. Great. Glad you asked that. And of course, as before, the good news is you don't have to see that whole expansion. The purpose of the sat library is to, just kind of to convince you that yes, there is an equivalence to the Boolean sat expression. But of course, you don't have to see all that. When you use the sat solver library, you can import the distinct utility, and then again tell it you have 3 integer variables, and then you add the constraint distinct A, B, and C. And then, of course, the next thing that they're useful for is, okay, you can satisfy constraints, but what if there's some flexibility in what the values are? You just want to find the settings of the variables to optimize some function. Like, let's say you had the variables A, B, C, D, possibly some more, and then you had some pre-existing constraints on them. Like maybe B has to be greater than C, maybe A has to be 4 times C, whatever. And then it turns out what you really want to maximize is 2A plus B. How do you represent that in the language of a constraint solver? Well, the good news is, if you were trying to maximize 2A plus B, an example, all you have to do, assuming you have all this infrastructure for solving constraint problems, you just add one more constraint, which is you pick some integer, say 10, and you add the constraint that 2A plus B is greater than n, and then you tell the sat solver to go to work on it, and if it finds that it's satisfiable, then you keep increasing n until it tells you it's not satisfiable anymore, and then just at the point where right at the point before it becomes unsatisfiable is the maximum value. I had mentioned before that Z3 is also a theorem prover, and so basically when you get to the point where you find an unsatisfiable value, then it has proven that there's no satisfiable value. And of course, as before, the good news is that there are utilities where when you define your problem, all you would have to do is instead of the solver function, you would use the optimize class, and then in that example, I define a variable value to be equal to a plus b, and then you use this utility opt.maximize, and then when you solve it, it makes sure to satisfy all the constraints and find the maximum value for 2a plus b subject to those constraints. So, and applying these, using the SatSolver utilities, you can build a Sudoku solver out of it. If you look at the repo, I show an example of writing a Sudoku solver using Z3. That's in pysudoku.py. Generally, how would you go about doing that? Well, you have to model the problem. In each Sudoku grid, and somebody jump in and tell me if I need to go over what Sudoku is. Kind of popular enough that I assumed it, but I can go over that. Just jump in and say what's Sudoku. But you would define some integer variable for each cell in a Sudoku problem. You would give it the constraint that all cells have to be 1 through 9. One of the integers 1 through 9. Cells in the same row are distinct. Cells in the same column are distinct. Cells in the same box are distinct. And then known cells must be equal to ... whatever the input is. So that is, when you get a Sudoku problem, it says certain cells are pre-assigned to some value. You just add those in as another constraint. And later, after the presentation, I can show you the code, and you can concretely see how you would input that as a using a SatSolver library like Z3. And then once you assigned it, it does all the work of solving it for you. Even better, there are logic puzzles that you might have used for. I went to that site right there, puzzlebaron.com, and pulled down an example problem, and I have some code showing how I would convert this into how I would solve this using a Z3. Again, that's an issue of making sure you've modeled it, defined your variables, translate your constraints into however you've modeled them. And if you have some time, I can dive into the reverse engineering problem that I worked with this. Let me see. Okay, that's it for the slides. I can go look at the code now. First, any questions? Anybody? I lose anybody so far?
I think this is a good something to start with, so it's good. You can go ahead with your demo unless someone else jumps in.
Okay. Well, yes. Let me go back to sharing my screen. As you saw the link to my repo, and you can pull down the code there. I'm going to pull some of these up and work through these problems. So let me start sharing my screen again.
We have all those links available at the Evening of Python Coding meetup page, so go there to download those later. Yeah.
There, so back sharing again. Make this a little bit bigger so blow it up. Okay. So let's start with one of the simpler ones. I have an integer inequality one. In this one, I give myself an arbitrary problem. Find x and y such that x times y is 30 and x plus y equals 12. There's some general boilerplate code around it, so you can handle the case of if it's not satisfiable, you can have it just print the indicator that's not satisfiable. Well, first the constraints themselves. You set the problem up. You define the variables. You add the constraints. In this case, I actually added some more constraints that I only wanted the solutions where x and y are greater than 0, and don't need any special language once you define the variables for adding the constraints. You just express them right there. And then once you want to extract out the answers, use the eval function to get the value. that it found when it solved the problem, and then you can print it out. So here, let's just run the code. Here, it found that solution. X equals 5 and y equals 6. Now, of course, it's kind of arbitrary that I said they had to be positive. I can actually take out those constraints and see what it finds. And there you go. It found another solution. It's probably easier when it doesn't have to, when they don't have to be positive. It's easier to have the sum be negative.
Silas, all of those that when you define those, first of all, it's like symbolic. It's like symbolic math. Like symbolic libraries usually define the symbolic variables, and I see you do it at the beginning, x and y, and only then you can write the expressions. Is it like something like SymPy that does something in the back that writes the symbolic expression?
I'm actually not sure how what goes on with respect to that. Just that, like, you have the library that understands the data types, and is specifically designed so that, like, you can just tell it that this is an integer, and then it'll understand future expressions when you call .add. I know behind the scenes it does whatever simplification it can find once it converts that into a the Boolean Satisfiability problem. Beyond that, I don't think I can don't have an answer for you.
No, so what I see here is like it's to me it seems very similar, like symbolic math, like SymPy, or like I don't know if everyone used MATLAB and Maple, the Maple thing that does this. Well, what they do is they take x's, now you defined it as some sort of creature, and later on it creates a symbolic link, and now you're at the equation, so it kind of internally knows it as symbolically. But this is what I see. Maybe I'm wrong. Anyway, go ahead. Sorry for this, but this.
No problem.
I hope you knew.
All right. So that's a simple inequality problem. Let's say we go into. Let's go to the next simplest one. Call it a simple optimization problem. Let me pull that up here. Oops, I ran it. Let's pull up the code for it. Oops. I already had it open. Okay. Oh, it's right there. Now, in this case, instead of doing initializing it as z.solver, I use the optimize utility. In this one, I went to the Wolfram site, and they had worked through the example, and I'm going to use that same example. It says it wants to maximize 12x plus 40y, subject to x plus y is less than or equal to 16, x plus 3y is less than 36, x and y are non-negative, and x is less than 10. See right down here, I translate all of those constraints. For simplicity, I said this thing, I refer to this thing that we're optimizing for as the value. And then we tell it we want to maximize that value. And then once it finds a solution, we extract out the x and y variables and print them. As usual, if it's not satisfiable, it'll just print unsat. Then we can run it. Let's say, what's great is you can add further constraints or subtract them as necessary. Like, let's say we didn't have to have x plus y less than 12. Oh, still the best solution. Let me go into a trickier one, which would be expressing Sudoku using one of these libraries. So how does it work? First thing we want to do is we want to define a big matrix. And with this line right here, what I do is define all of the cells in it, basically iterate. I define size to be 9, and then it iterates, goes through 0 through 8. So in this case, did I see this spell out somewhere? In this case, it would create this matrix. Each row corresponds to a row of the Sudoku problem. Down here is what it would look like to say that for every value in that A matrix, it has to be greater than 0 and less than 10. Down here, what it's doing is, let's see, we're iterating over each row, and then for each row, iterating over all the values in it and saying that all the values in that row have to be distinct. Similar concept for the columns. That is, we iterate over every column in it and say all the rows in that same column have to have distinct values. Basically saying you can't have two of the same integers in the same column. A little bit trickier to do the box constraint, but the way I did it here was I iterated over the boxes, and then I used the index of the box to identify all of the cells within that box. So you imagine you're on the box in row 0, box in column 0. You would locate all of the other individual cells of it. Concretely, let's say I was looking at box, see in the top row of boxes, I would have box 0, 1, 2. I would locate all of the cells in that box relative to the indexes of the box. Kind of talking over myself, but basically that's what it would look like. Now the Sudoku problem that I solved, you want to blow it up, represented it in ASCII right here. You can see the boxes. Actually, let me clear that up a little bit. The integers you see there are those given in the problem. Question marks are those not given. And so at that point, it's just a matter of adding the given values as additional constraints to the problem. Put the indexes of the columns and indexes of the rows to make it easier to read. So for example, if you were going to add that part of the problem constraints this cell to be 9, then you would add the constraint down here as A02 is equal to 9. That is, row 0, column 2 is equal to 9. Repeat that process for all of them, and then you have it fully constrained, and then you can just tell it to solve it. Here, the only trick is having it convert the output. I have it look up each value of the solution and put them into a matrix, and then print it out. So let's run that one. Gives you your solution. You know that it satisfied the constraint that the top row has this 9, 8, 5, 6. And just for fun, we know that this very bottom corner value in the solution is 3. We can add the constraint that that value has to be 9. And if we do that, it'll say it's unsatisfiable, because that was the only way to satisfy it. And if we added one more constraint, we made it unsatisfiable. Everybody with me still?
Oh yeah. Yeah, this is good. Thank you.
Thank you.
Question for Rob.
Oh, go ahead.
You want to stop? Yeah.
So, what if there's more than one solution? It may not be applicable to Sudoku, but
True. Generally, when they give you a Sudoku problem, they'll make it so that there is only one solution. But if they under-constrain the problem, then basically there's no guarantee which solution you'll get. It'll just output one of those solutions because it just works until it finds some solution that satisfies all the constraints. Now, in that case, if you wanted to find every solution, well, with this, as it works, generally the trick to making sure you get all the solutions is to run it one time, you find your first solution, and then you can go back and then add one more constraint, which is to say, the solution is not this one. That is, you add one more constraint saying, give me a solution, but not the one that I just found. And then you run it again, and then if there are more solutions, it'll give you that one. Is how you would handle it in terms of getting all the answers. Did that answer your question?
Probably yes.
Okay.
I assume that probably muted. I have another question.
Sure.
Here, I'll show myself. So,
do we need to
whoever
switch to your
asks the
screen?
question, show themselves if they're uncomfortable with it. It will be nicer. This way we know who's asking. I was mentioning before. Did you ever see other symbolic libraries like Maple or like Mathematica or?
Okay.
Because
I work with
SATsolver
those.
seems to be very close, and I'm trying to figure out what the difference is. Like I noticed in SATsolvers you use integers. Is this the difference?
You don't have to use integers. In fact, you can. Let's see. Go back to one of these. This symbol optimization one, I actually said real, which allows it to be floating point values. I hadn't actually used Maple in a long time, but there's a lot of similar functionality in inputting something and telling it to satisfy constraints.
Okay.
The advantage of using Z3 would be you can use all of the expressiveness that you're comfortable with in Python, all the iteration. If you want to input you want to input something that follows a pattern, and you don't want to tediously, spell them all out. And if you already know Python, you can use its iteration capabilities to help you set it up. So you kind of get to apply all of your Python knowledge. Sorry, talking too long.
However, this only solves the problem. It doesn't go ahead and do things like differentiation, integration, or stuff like that. Correct? It's just a solver of a set of equations.
Correct. It's just solving a set of equations. It wouldn't be like solving a differential equation where it would get a graph as the result. Although I'm pretty sure you can define this in a way so that you find the solution if there is a solution in closed form.
One more question. Sorry for taking that so long, but what about in case the like infinite number of solutions? Let's say it like this. Will it always return to you the same thing, or is there a random seed or something that makes it give out a new one each time or a different one?
I actually don't know that definitively off the top of my head. In my experience, if it's under constrained, it generally give the same solution the first time, but I don't know if that's guaranteed, and I don't know if they use randomization.
I assume, but some sort of randomization happens, hashing or something, otherwise it won't be giving the same number each time. But I don't know what happens underneath the hood there as well. So it was a nice question, and you gave a nice answer. I think that at this point, anyone has more questions? I see myself. Anyone more questions? Going once? Going twice? Going 3 times? Okay. In that case...
Hey, I have a question.
Okay.
What are the limits here? How big a space it can be to make it reasonably find the solution?
I actually don't know that either off the top of my head. I can say that generally you're still set up to the same constraints you would face without. Like it doesn't provide a speed up over the best solvers for a specific problem. You can get into situations where it's just overloaded, and with the resources you give it, it can't solve it. It also has sort of an advantage in that it intelligently looks for the solution. So if there are easy simplifications it can do to the search space, it'll take advantage of those. But as you don't know concretely how many clauses behind the scenes it converts to before you start running into trouble. I do know that on the general one equivalent way to express SAT solvers is as 3-sat. which is basically the and of a bunch of 3-value OR statements. And there are certain parameters they know where the problem gets difficult, but specifics I don't know. The good news is, in the general case, you probably won't run into a case where you find that you've converted it into one of the hardest NP-complete problems with that size. So generally, it'll be fast. But unfortunately, I can't give much better answer in terms of how many variables.
Can you limit it in by the way of time, saying, let's say, 10 seconds, and if you didn't find it 10 seconds, give up?
I don't know if it has any that specific functionality. Can of course always just like set a timer to kill the program if it's not finished by then, but that's kind of a hack onto it.
Alrighty, thank you.
Any more questions?
Right. If we have time permitting, I can show another more practical problem I used this for, which was an reverse engineering. I gave this other
Go ahead.
gave this other presentation. Let me skip to the interesting part of it, which is okay. Basically, came into this problem where I want to add some arbitrary amount to a register, but I can only use bytes from the alphanumeric space. As a reminder, these are the hex alphanumeric bytes. Let me express this sort of problem first in terms of base 10. If you look down here, what if you ran into a case where you're operating modulo 100? That is, imagine you have some kind of counter that only goes 0 to 99, and if you add 1 to 99, it rolls back over to 0. That would be, in the lingo, operating modulo 100. And modulo 100, if you add 100, that's the same as adding 0. It just rolls back to the beginning. Let's say I had a problem where I want to add 8, but I'm only allowed to add 12 at a time. Could I still add 8? As you see, there's a solution right below it. If you add 12 9 times, you're adding 108, which is the same thing as adding 8 mod 100, because that first 100 wraps around, and what you're left with just adding 8. Now imagine that we have that same problem. We want to add some arbitrary value, and we're adding it in 2 bytes. We're adding it in integers that have the size 2 bytes. Each byte must be from this hex alphanumeric space. Just like in this problem, we were limited to only adding 12. In this case, any number we add must be made up of the bytes on this list. So to give an example of the problem solved, and again, this is working in hexadecimal. Let's say what I really want to do is add hex 1000. 1000 expressed in terms of these 2 bytes, those are outside the alphanumeric range. As it turns out, and this gets kind of nutty, you can break it into these 3 values and exploit the rollover. Basically, this will be greater than the maximum 2-byte integer, but it'll roll back over. You can break out a hex calculator. Break out a hex calculator. And there, the sum of those is hex 11000. But if we're operating on 2-byte words, everything after this digit goes away. So because of rollover, we would be left with just that 1,000 there. So how would you do that? If I pull it up. First, is everybody clear what I'm trying to do? What I'm doing here is since I'm working on registers that are only 2 bytes large, I can tell Z3 that each of my numbers is only 16 bits in size, and so it knows that any addition you do with them will have that rollover effect, where if you exceed the maximum value you can represent, it rolls back over to 0. I can tell it that each of these words are made up of concatenating 2 bytes. I can tell it that all of those bytes have to be in the alphanumeric ASCII range. And then it'll find solutions for me. Earlier you saw I was running it there, and then that gives me my solution. Like here, if I wanted to add hex 26, tells me I can break it into these 4 additions. Anyway, getting a little more into the weeds, I can probably break that off and do a separate session for that, because that's getting kind of complicated, but there you go.
So what you're suggesting is that this is a security problem, or like buffer overrun or something like this that you're trying to resolve?
Yes, exactly. The specific problem was you're allowed to buffer overrun and inject malicious code under the constraint that it will reject non-alphanumeric input. And as I was working that, I found what can I do? Turns out you can on that architecture I was working. The instructions for adding to the stack pointer are in the alphanumeric range, but only if the value that you're adding is itself in the alphanumeric range.
So
hence that.
This way you can use it to block those exploits by knowing how people can exploit this, is what you're saying?
Yes, you would show, well, it would effectively show that like limiting them to alphanumeric inputs is not enough, because they can still do almost whatever they want in that format.
Okay, so they basically chose that this architecture should be redesigned.
Oh, well, that would be one way to do it, yes. Make sure that like the adding to the stack pointer is not in the alphanumeric range would, yes, be one way to patch this.
Okay. Silas, I think unless people have more questions, in which case they should unmute themselves and ask. Otherwise, you should show yourself, and we should actually all show ourselves and tell you thank you, clap or something, because you've done a very good job in explaining SAT solvers.
Thank you.
Nice demo. So I would clap, but I hope others will join me. Unmute yourselves. Ah, here's Danny. Okay.
Good job, thank you.
Thank you.
Okay.
Even though I didn't understand most of it.
Stay online. I'm gonna stop the recording now, but we're gonna continue.